So, Drew, you can go ahead and introduce yourself and share your screen and start your talk.
Great. Thank you, Dan. Thank you for the opportunity to speak. So this is a project in chromatic homotopy theory, which is, I guess, what I started life out interested in. And yeah, like Charles, I guess now I would say I'm interested in lots of things, but this was a project from a few years ago about computing some Picard groups in chromatic homotopy theory. And so everything I will talk about is joint with Akil and Vesna. So in fact, a lot of the foundations are coming from their original paper on the Picard group of TMF and related things. So if I can, there we go. All right, give the 1 minute introduction to what the Picard group is and what we're trying to do. So we'll always start with some suitable category. It's symmetric monoidal, so it has a tensor product and a unit. And then, so we're going to look at the Picard group, which is a group of isomorphism classes of invertible objects under this tensor product. So I have some object M, can I find another object, it's inverse, M inverse, such that when I tensor them together, I get this monoidal unit 1. So you can do this in any symmetric monoidal category really, but today we're just going to focus on, so R will be some nice ring spectrum with its usual, its smash product over R. The unit is of course R. Or we can take some Bousfield localization. So this is what this means, the category of E local R modules for some spectrum E. And in general, if I take two E-local modules together and tensor them together, it need not be E-local anymore. So I just have to relocalize it. And the unit is the E-localization of R. So I'm just going to denote these as either pic R or pic subscript ER in the E-local case. Okay, so what's the first example? Well, we can take, for our ring spectrum, we can just take the sphere spectrum. So this will be modules of the sphere spectrum, which will just be the Picard group of the stable homotopy category itself. And so we know that for every sphere, well, for SM, I can always find S minus M. When I tensor them together, I just get the unit. And so this gives a Z summoned in the Picard group, and it turns out that this is all there is. So it's just a copy of the integers. So it's kind of boring, I guess. But the inside of Mike Hopkins, or the idea of Mike Hopkins, is that if we take this certain localization, so Kn here is Morava K theory, and there's sort of a field object in the stable homotopy category. And if we look at Kn local invertible modules, it becomes much more interesting. And so for these Kn's, there's one for every N and every P, of course. There's no P in the notation, and it's hiding there. You can see even when N equals 1 and the prime is bigger than 2, the Picard group really has this p-adic factor, and it's a really, these are sort of p-adic interpolations of spheres, if you like, generating this. And these calculations, these groups are really, really hard to compute. So we know them fully at N equals 1 for all primes. At height 2, it's fully calculated and published for primes greater than 3. And I think the P equals 2 case is work in progress, and it might be solved or soon to be solved anyway.
Hi, Drew, this is Dan Isaacson. Can you say simply what the N equals 1, P equals 2 case looks like?
Yeah, so it's, let's see, I think it's the Z2 cross, so the 2 adics cross Z mod 2 cross Z mod 4. So it has the same sort of form as this, as the P greater than 2 case, except it has one extra factor, this factor of Z mod 2, and this is sort of the exotic part of the Picard group, it's called. And yeah, so when the prime is large compared to N, this calculation always breaks up for the K-local Picard group into sort of an algebraic part and then another part. And when the prime is large compared to n, it's known it's just algebraic. But when the prime is small, then computing these exotic parts is actually kind of interesting. And so n equals 1, p equals 2, the exotic part is this extra z mod 2. And it's for those who know these things, it's like the K1 localization of the question mark complex is this sort of exotic element at n equals 1, p equals 2. All right, so the goal of what I will talk about today is some sort of approximation to pick n. So at higher heights, can we say anything? And I guess, so for the K and local Picard group, even basic structural results are not even known. So there's this question in Hovey-Strickland's memoir, and I think it's still not known as to whether it's finitely generated as like a p-adic group. So there could be an infinite product of copies of ZPs, and no one knows how to rule this out just yet. But we will stick to slightly easier things. So the spectra we'll look at come from Morava E theory. So this is a certain ring spectrum in homotopy. It has this very nice coefficient ring. So it's the Witt vectors over fp to the n join these power series variables u1 up to un minus 1. They all live in degree 0, and the degree of u is 2 or minus 2, depending on who you talk to. But so this ring E0, the Witt vectors on this power series, it's a complete local Noetherian ring. It's this u1 up to un minus 1 are regular, so it's a really nice ring. And well, it's a bit complicated to say where this comes from, but where the construction of Morava E theory is coming from the theory of formal groups. And by this, there's a certain profinite group that acts on En. And so it's also known then that it acts on the spectrum En. And it acts in such a nice way. And well, in general, it's not known. It's a profinite group how you would form the homotopy fixed point. But Devenitz of Hopkins have proved that for any closed subgroup of this, you can define something that deserves the name the homotopy fixed points. And when G is just a regular finite group, this agrees with the usual construction. So, but the connection to this, what I was talking about before with the Kn local homotopy, is that if you take the full, so this Gn is the Morava stabilizer group. If you form this homotopy fixed points with respect to the thing itself, you just get this Kn localization of the sphere spectrum out. So that's a super quick introduction to chromatic homotopy theory. So here's the example. So you take a maximal finite subgroup, then these are the higher real K theories that I mentioned in the introduction to the talk. And why is this? Okay, so if you take the simplest case, n equals 1, p equals 2, then this Morava stabilizer group is just the units in the two adics. And so this decomposes as a copy of the two adics cross z mod 2, or C2 as I read it here, as I wrote it here. So the maximal finite subgroup is just C2. Then this homotopy fixed point spectra is nothing other than two complete real K theory. So when you go to higher heights, you take the maximal finite subgroups. It's natural to call these the higher real K theories. Okay, so from this equivalence before, that the homotopy fixed points with respect to the full Morava stabilizer group is just the Kn local sphere. If we pick a maximal finite subgroup or any finite subgroup, we get a map like this from the homotopy fixed points of the Gn to just K. So what we're going to do today is we fix n equals p minus 1, pick any finite subgroup, and try and compute this Picard group here of modules over the En HK, this spectrum. So the reason we fix n equals p minus 1 is, well, when p minus 1 divides n, this is essentially the interesting case in chromatic homotopy theory. If this is not true, then things tend to collapse, and the Picard group in this case becomes kind of boring. So here's the punchline, is that we don't see anything interesting. So if we pick a prime and let n equals p minus 1, take any finite subgroup, then so it's known that these are all, the homotopy of these is cyclic, as we'll see, but the Picard group is just the suspensions of this. So when the Picard group of the Kn local category itself, as we saw back, it's quite interesting. We can't see really any of the interesting stuff in these smaller Picard groups, unfortunately. But the calculation itself is still kind of interesting. So this is the approach of using Picard spectra. So this comes from Akil and Vesna's work, and also work of David Gepner and Tyler Lawson. So you pick some nice category.
Drew, sorry to interrupt you. It looks like Sean Tilson has a question. Sean, okay. Go ahead.
Hi, Drew. And on the previous slide, you said that the group was cyclic. Can you get different cyclic groups for different finite subgroups?
Yeah, because they have different periodicity depending on the group itself. So
okay.
Yeah, so if I pick at height 2 or something, I can pick at any height I can just pick CP, and we'll see this is, I think, 2p squared periodic. But if I pick the maximal finite one, it's 2p squared n squared periodic. So it does change depending exactly on which group I pick.
But you never get an infinite cyclic group.
No, that's right. All these finite subgroups always have periodic cohomology, basically. Periodic homotopy, sorry.
Okay, thanks.
Yeah, the periodicity comes from the fact that E star itself is 2 periodic, and then you run the homotopy fixed point spectral sequence, and it's known that this has a vanishing line at some finite stage. So you have to get some periodicity then. All right. So yeah, I have my nice symmetric monoidal category, and then in the paper of Akil and Vesna or of Tyler and David, they tell you can build this group-like E-infinity space pic C, which sort of, it remembers more information than just the fact that a module is invertible. And it's group-like E-infinity space, so it's the D-looping of this connective spectrum pic C. And this spectrum has the following very, very nice properties. So its pi naught is just the Picard group of the category that we're considering. Its pi 1 is the units in pi naught, the units of the endomorphisms. And yeah, for I greater than 1, it's just a shift of then the homotopy groups of the endomorphism. So in the case we consider when C is just mod R for a ring spectrum, this N1 is just R itself. So it's the units in pi naught, and then it's just a shift of the homotopy groups. Oops. So this last comment here just is that this pic is just a de-looping of the space of units. So you see the units just has its homotopy groups are these here. So we'll use this at some stage. We work rather with the units rather than the Picard spectrum. All right, so the way we approach this calculation is via Galois theory. So let me just quickly say something about that. So this is Rogner's version of Galois theory for ring spectra now. So now A and B are ring spectra. G is acting on B in such a way that the canonical map from A to the homotopy fixed points on B is an equivalence. And also if I form this tensor product, so G is a finite group here, of B with itself over A, I just get G copies of B. So this is a Galois extension. Particularly nice Galois extensions are the ones that are called faithful. So faithful just means that if I have an A module M, and I tensor down to B, if it's contractible there, then it was contractible to begin with. All right, and then the theory, I don't know who to attribute this to. Find it lots of people. So there's Rogner's, it's in Leonard Meyer's thesis, it's Akil and Vesner's paper, Tyler Lawson and David Gepner's paper. So attributed to all of them if you like, but it just says that the category of B modules inherits a G action via the action on B. And if you have this nice faithful G Galois extension, the homotopy fixed points formed in this category is equivalent to the category of A modules itself. Okay, so the example of the Galois extension that we will consider, so pick a finite subgroup of the stabilizer group, then there's a faithful Galois extension from this homotopy fixed point spectrum down to En. Okay, so in his book, Rogner's proves that this is a Kn local Galois extension. So the same as this here when you Kn localize everything. But by work of Akil and Leonard Meyer, if G is finite, you actually don't need to Kn localize this to get a Galois extension. So that will be somewhat important. All right, so the reason we introduce Galois extensions is the following result. So if you have a faithful Galois extension, and then basically this equivalence you had before says you can apply pick to this. So have this pick spectrum of A is, well, it's almost the homotopy fixed points of the pick spectrum of B. The problem is this thing is no longer connective, but that's just fixed by just taking, the connective cover. So that's just what this little symbol here means. Ugh. Sorry. All right. So coming from the homotopy fixed points on pick B, we get a spectral sequence. So it starts from the cohomology of G with coefficients in pi t of pick B, and it converges to the homotopy fixed points of the G action. But from this result here that says, well, in positive degrees, the homotopy of this side is just the homotopy of this side. This says that when t equals s, i.e. pi 0 of this thing, it's just pi naught of pick A, but we know that pi naught of pick A is just the Picard group of A modules itself. Okay, and so the idea is that in general, B might be easier for some reason. Its homotopy groups are concentrated in even degrees and regular, then the Picard group of these things is known. Whereas in A, things could be much more complicated in A, but then maybe the descent spectral sequence is understandable. Okay, so this is exactly how we're going to try and compute this today. So I'm going to work at n equals p minus 1, and we're going to use this Galois extension down here to try and compute this Picard spectral sequence here. Okay, so I said before we're going to do this here, G is any finite subgroup of the stabilizer group. So this stabilizer group was a certain semi-direct product of this, the little stabilizer group and the Galois group. So if I take any finite subgroup of the big stabilizer group, it fits into an extension of this form. So this GS here, I just take my group and intersect with this smaller stabilizer group, and then I get this extension. And so we want to do a reduction. So the reduction that we proved is that, well, if we can prove that this Picard group here, coming from the homotopy fixed points, is just cyclic, then so is this bigger one. Yeah, exactly as it says there. Yeah, so how do we prove this? Well, from this big group to the one intersected with the stabilizer group, it turns out to actually be very nice. So it's a Galois extension even on homotopy. So after applying pi naught, this map is a tile, and well, you have this nice decomposition on homotopy groups. And I mean, what you do then is so you start with a, that's right. So you pick some module, some invertible guy in here, and then you tensor down, and then you end up with something in this Picard group. By assumption, this is cyclic, and then using this point here, you can show that this also must have just been a suspension of eNHG to begin with. So that is the first reduction. The second reduction is that if we then, so now I pick my G to be something inside of this smaller stabilizer group. So using this first reduction, and then I just pick some P-silo subgroup of that. And now if the Picard group of this smaller, with respect to this smaller subgroup is cyclic, again, generated just by the suspension, then the Picard group of the whole thing, this bigger group, is cyclic. And yeah, I guess the idea here is that by sort of a general result in the paper by Akil and Vesna, it's known that this is a torsion group, and to prove this, you just study the Q torsion for each Q, and it just naturally breaks into two cases: when Q is P and when Q is not P. And yeah, you just do it, and you get this result. So when n equals P minus 1, so the subgroups of Sn have been classified by Hewitt, and in this particular case, combining these two theorems, well, we can reduce to the P-silo subgroup. It just turns out that this is just, it's just CP. So in order to prove the result that we claim for any finite subgroup, it's actually just enough to prove this for the case where G is CP itself. So in this case, let's see, from this Picard spectrum, we'll note that the homotopy groups, once I is greater than 1, are just the homotopy groups of the spectrum itself. So to understand this descent spectral sequence, we should first understand the ordinary descent spectral sequence. So this was calculated by Hopkins and Miller and Maholwald. Sometimes it's a little hard to find details, but so the result is that modulo the image of the transfer. So there's some stuff contributing to H naught that we can just ignore. Yes, it's just this polynomial ring over Fp to the n on 3 classes. So alpha, beta, and then delta. This is our periodicity operator. So alpha lies in degree 1 to n, beta. So n equals P minus 1 here, I should say, and P is odd. So that will be the assumption these previous reduction theorems did not rely on any prime. This is true for all n and all p. But here we are fixing n equals P minus 1. So these alpha and beta, for those who have, who are familiar with odd primary stable homotopy, are just the image of the classes, I think usually denoted alpha 1 and beta 1. And so it's known, we have these total differentials in stable homotopy theory, and there's a map down from the homotopy groups of the sphere to the homotopy groups of what we're computing, and this gives you the differentials in this spectral sequence. So in fact, it's determined entirely by these two differentials here, and so I'll show the picture in a moment, but you can see that, well, this periodicity operator delta dies, but delta to the P survives this spectral sequence, and the homotopy groups then become 2P squared periodic. So what this does is this tells us, well, this sets a lower bound on the Picard group. All the 2P squared powers of the unit must be, they're all invertible elements. So it must have order at least 2P squared. Okay, so here's what it is.
Drew, it's
Yep.
Sean. I have a question about the last slide, about something you said on the last slide.
This one?
You're talking about the differentials from the homotopy groups of spheres,
Yep.
and pushing them forward. What
Yep.
spectral sequence is that you're pushing them forward to the homotopy fixed point spectral sequence?
From the Adams-Novikov spectral sequence, I think. I think you have to use...
Maybe I'll ask you at the end of the talk how that goes.
Yeah, I think you have to... Yeah, you can use the Morava's change of rings theorem to reduce to the homotopy fixed point spectral sequence, basically.
Ah, okay. All right. Thank you very much.
No problem. Okay, so here's the picture when n equals 2, p equals 3. So you can see this class alpha, the class beta, and this class delta, and then I guess if you've looked at these before, this you might have seen these sort of charts, but if not, it's probably not telling you much. So I will just move on. Here is what I wanted to say. Actually, this is why I included it. So this is an Adams index chart. So it's T minus S along the bottom and then S along the vertical axes. And so from this comparison from the Picard spectrum to just the ordinary spectrum, so everything above the T equals 2 line will also be on the E2 term of the Picard spectral sequence. So let's see if it says I can annotate along here. So yeah, so everything on this side is also in the Picard spectral sequence. It just gets shifted by one to the right. So in particular, and remember we're interested in pi naught of the Picard spectral sequence. So there's this class here will move into the 0 stem, and so this will be a possible contributor to the Picard group. And this class is one to remember. I'll call it E1. It'll come up later. All right. I'll get rid of those. Okay, so this is just what I said here. For t greater than 2, which was this diagonal line, the E2 term is just the same as that as the Picard spectral sequence. Okay, the question is, what about the differentials? So we know all the differentials here. Can we import the differentials into the Picard spectral sequence? Okay, and this is the result that we proved. So if you have a Galois extension where p minus 1 factorial is invertible in pi naught, then there is a certain range where you can import the differentials from the Picard spectral sequence, from the ordinary homotopy fixed point spectral sequence into the Picard spectral sequence. And I'll explain a little bit more over the following slides exactly what this is, but we obtain a formula for the first differential outside this range. Okay. So this is the setup. So of how to prove this theorem. So our bullet is some co-simplicial E infinity ring, and we have 2 spectral sequences. So a Bausfield-Kahn spectral sequence for our bullet and for GR1 of our bullet. So now we work with this GR1 rather than pick, and this just stops this shift by 1 occurring. And it converges, to T minus S of the tote spectrum, the totalization. Okay, so in their sort of foundational paper, Vesner and Akil proved that for any n greater than 2, you just have this equivalence of spectra. So in the range from n to 2n minus 1, GR1 of our bullet, just the same as our bullet. And putting pick in, this just shifts things around. But the net result of this was that in a certain range, you can import differentials from the ordinary additive spectral sequence into the Picard spectral sequence. We had something a little bit special here. We know that on homotopy in pi naught, we have this condition that our ring is Z adjoined 1 on p minus 1 factorial local. And the idea is that there should be a greater range in which we can import differentials when we have this extra condition. Okay, and so to prove this, the strategy is basically exactly the same as in the first paper. So we're given some t greater than or equal to 2 and an element in this here. So this is the minus 1 stem, because this is the stem we're interested in, because in the Picard spectral sequence, everything gets shifted by 1 to the right. So this will be the 0 stem. And we have some class that survives to the EK page of the spectral sequence. This is our assumption. And then this is the theorem. So if K is less than or equal to this here, then this class, yeah, exactly. It's the differentials from the additive spectral sequence can be imported into the, now this is the GL1 spectral sequence. This is what this cross is for. But perhaps the more interesting thing is that if T is even, and then, so this is the next, this is the differential first differential that we can't import. We have this formula here. So it says that it's the same as the additive differential plus this little correction factor. So this beta P T on 2 is some sort of cohomology operation, if you like. And it's determined, we determined it up to this unit in FP. With a little more work, we probably could have figured out exactly what the unit was, but we didn't need it. This was enough. So we sort of stopped this here. And what's the idea? So how do you prove this? Yeah, so we construct the universal example of such a cosimplicial ring together with a class in this degree here, and study the two Bausfield-Kahn spectral sequences, so the ordinary one and the GL1 one. And by an argument that's in the first paper, because it's universal, it's enough to study what happens in this spectral sequence itself. So, and it turns out that if K is less than or equal to P minus 1 times T, the only possible target for this differential D in the GL1 spectral sequence is just this group here, Z adjoined 1 on P minus 1 factorial. And this allows you to identify the D differential with just the additive one. In this first case that we can't import the differential, this is because there is a possible, so there's an extra FP factor that occurs. And this tells you by universality that there must be a formula like this, that the GL1 differential is just, okay, well, there's an A factor here, but we also prove that this is 1. So it's A times dk plus zeta times this. Okay, this cohomology operation is what generates this FP factor. We also have to show that. It's not clear immediately that this zeta should just not be 0, but to show that it's non-zero, well, you just need to find a single example where the two differentials in the additive and the GL1 spectral sequence don't agree. And we do that, and then hence we know that there must be a non-zero differential. I mean, that this must be non-zero. Okay. So let's go back to the picture. Okay. So again, we were looking at this minus 1 stem, and it turns out there are infinitely many classes going up this way. In the additive spectral sequence, they are all either targets or sources of differentials. And by this previous formula, all the differentials, except for this class that I called E1, they could all be imported into the Picard spectral sequence. So this immediately tells you that everything above here just dies. This class E1 is more interesting. So I didn't explicitly say here, but the black dot with the circle around it means it's a copy of FP to the N. And what this formula shows is that in the Picard spectral sequence, well, it can't be bigger than actually FP. So it could be 0, but it can't be FP to the N itself. And the reason that this works, and the reason we actually didn't need to figure out exactly what this zeta factor here was just the result that this power operation or this cohomology operation has this semi-linearity property. So for any A in FP to the N, if I multiply this class E1 by A, I can pull it out, but now it's A to the power of P in here. And you can use this to show that this kernel of this differential is at most FP. So this is good. So we've cut this FP to the N down to a smaller group, to FP. And we've got rid of everything above that. So this actually, let's get back to it again. This is actually now leaves us with only two other contributions. So we had this class here. There's nothing else in these things that can contribute in the zero stem. So we just have to work out the H0 and H1 terms. So these are a little bit harder. Well, the H1 is harder, I guess. All right, so in filtration 0, so this is, remember T equals S here, so it's H0 of CP with pi naught of pic En. So pi naught of pic En is just the Picard group of invertible En modules. And so Baker and Richter have this theorem that says, well, if your ring is concentrated in even degrees and is nice enough, which is, it's Noetherian regular local ring, then the Picard group is just the same as the Picard group of E star modules. So it's algebraic. And in this case, this ring is nice enough that we can know that it's just too periodic. And so by this Baker-Richter result, the Picard group is just Z mod 2. So in filtration 0, we just get a Z mod 2 term. Okay, so the final thing we have to work out is the one, filtration 1. So this is H1 of CP with coefficients in pi 1 pic En. Or in other words, this is pi naught of the units in En. So it's H1 of CP with the coefficients in the units. Okay, and so this was kind of hard to compute actually. So the proposition is that it's turns out to be it's Z mod P generated by the twofold suspension of E. Okay, so how do we compute this? So just a reminder that so E naught was the Witt vectors that joined FP to the N, joined these power series variables U1 up to U minus N minus 1. It's a complete local ring. This maximal ideal is P and all these U1s, these UIs. So we get two spectral sequences associated to the M-adic filtration. So one is just the ordinary additive spectral sequence, which will compute just the ordinary cohomology, and the other one is the one that we'll be interested in, which will compute the cohomology of the units. And the point is that the E1 terms are very similar. So for J greater than or equal to 0, there's a CP equivariant isomorphism between these the coefficients that we use here. And this basically means that if you understand this spectral sequence, then you can get the E1 term here essentially by just deleting one row. And then the second part is to work out all the differentials. Okay, so fortunately, this spectral sequence is sort of understood. It's in kind of unpublished work of Hopkins and Miller, but we were kind of able to back calculate what the answer has to be. And again, modulo is some stuff that we don't really care about. It's the cohomology of CP, the ordinary group cohomology with coefficients in FP to the N, joined some classes and some relations. So again, here's a picture when N equals 2 and P equals 3. And so this is drawn, let's see, this is filtration degree is along vertical, and this is HI along the bottom here. So for example, in H2, the only class that survives is this class B here. And this is, let's go back again, my favorite slide. So what we're computing here is the cohomology in E naught. So this is this T equals 0 line. And this class here is just this class corresponding to B. Here's B squared and B cubed. So here that there's nothing in H1 or H3 or the odd H's. And this is corresponding to the fact that everything in H1 here is dying, and then similar for H3 and etc. Okay. Okay, again, so the question again is, can we import the differentials from this additive spectral sequence into the multiplicative one? Because we know the E1 term is going to be the same, we just delete this row down here, but what about the differentials? Okay, we're again in the situation where R, well, now we're going to let R be a Z-adjoined 1 on P minus 1 factorial algebra. And we have these nice P truncated exponential and logarithms here. So find in the usual way you define the exponential function and the logarithm in calculus when you do Taylor series, but we can just truncate them at the P minus first term, I guess, or the P term. So why do we care about this? Well, so we choose some ideal inside of R. If the ideal is I to the P equals 0, then this map gives a group isomorphism between I and 1 plus I inside the units, the inverse given by the log function. Okay, and so in the case we're interested in, this gives you an isomorphism of groups between 1 plus, so instead of just k plus 1 down here, now we can take p to the k, and this is isomorphic to this. And if you actually just study these two spectral sequences here and unwind what's actually happening on the higher pages, this fact here tells you that when you have a ring R like this, you can import the additive differentials whenever the filtration degree is at least 2. Okay, so above this line here, we can import all the differentials. So this class also dies, I guess. We didn't draw this picture very well, but so this means that the only possible contribution to H1, which is what we are trying to compute, can come from this class V primed here. Okay, so how do we get at this class V prime? Okay, this is what I just said. Again, we produce a formula for the first differential outside this range. So again, it's the additive differential plus, well, in this case, we actually worked out the constant. It was -1, some power operation applied to the class. I guess I don't have there's no easy description of what we did here. We just really just thought about this in terms of cycles, and it really on the chain level, if you will, and explicitly what happens. I guess it's really sort of boiled down to the fact that of studying the failure of this exponential function to actually be a group homomorphism was a key point. But we've got this formula, and this also has this same semi-linearity property as before. And again, it's actually a very similar analysis, shows that although this class V prime here started life as an FP to the N, after applying this formula, it can be at most an FP. But in this case, well, to calculate this group is generated by sigma 2, and by periodicity we know that it must be at least then a Z mod P, because it's 2P squared periodic. So it's both an upper bound and a lower bound. So this group actually must just be Z mod P. Okay, so now we've actually computed everything that we can for this spectral sequence. So here's the picture of the Picard spectral sequence. So here's my class E1 that I've been talking about. And here's this red line showing this differential that we sort of understand. And here's one of these classes that was not shown before. You can see that it dies, and everything else dies here. This cross here was the Z mod 2 we got, and this dot was a Z mod P. Okay, so now and then, yeah, we didn't actually know what is going on in these question marks over here, but we can already see now. Okay, so in filtration degree 0, we have a group of order at most 2. Filtration degree 1, we have a group of order P, and in filtration degree 2P minus 1, we have a group of order at most P. So this was here, this was a Z mod 2, Z mod P, and this was also at most a Z mod P. If you put those together, you get an upper bound on the Picard group of, it's a cyclic group of order 2P squared. But as I said a while ago, 2P squared is also a lower bound because the homotopy groups are 2P squared periodic. So it's an upper bound and a lower bound. This means this Picard group is actually just Z mod 2P squared. And then because we've proved the result for CP, we've then proved it for all finite groups at this particular height. And I believe that is actually the end. So, see.
Okay, terrific. First of all, let me unmute everyone. Unmute all, sorry, give me a second. Okay, let's thank him. First of all, let's thank you. Thank you, Drew, yay. Okay, I'm going to re-mute everyone. And let me unmute Drew. Okay, and open it up for questions.
Hi, Drew. This is Sean.
Hi, Sean.
Is these power operations that you get? These are just like algebraic power operations, since you're looking at the cohomology of a group.
That's right.
Okay.
Yep. They're to do with, yeah, you can, I guess, look in the paper or ask afterwards for more details. They're to do with derived powers of symmetric functors. Some old work of Pretty we had to use to actually work out what they are.
Really?
Yeah.
When you say symmetric functors, you don't mean anything that's like related to the stuff from Bousfield's thesis? You mean...
I don't know. Yeah, ask me afterwards and then we'll see.
Okay.
Okay, other questions?
I do have another question, sorry.
Okay. Go ahead, Sean.
There's another notion of GL. There's a graded unit spectrum that's used to understand topological log structures.
Uh-huh.
It's been developed by Rockness, Sagave, and Schlichtkroll.
Yep.
They're in the relationship between this GL that you worked with and Pick here. I'm curious if you've thought at all about a sort of graded Picard group in analogy to the graded unit spectrum.
I haven't, no.
Okay.
Yeah, and I'm not familiar enough with this graded GL1 either to say anything, unfortunately.
Okay. So, all right, thanks.
Okay, other questions? All right, well, let's go ahead. I'm going to unmute everyone again. We'll thank Drew one more time. Thanks very much. Our next meeting is in 2 weeks, and Nico Naumann will be the speaker. Thanks very much, guys. Bye.